Hi students, in the earlier chapters we'd learnt about the force of friction. But how much friction acts on a block when you apply a force F on it? Also, if you apply a certain force on a block placed on a table, will the block be still or will it start moving despite the friction force? In fact, what exactly is the friction force? We learn about all this and more in this chapter, friction. So let's first understand what friction is exactly. When two surfaces in contact move relative to each other, or when they have a tendency to move relative to each other, then at the surface of contact there appears a force which opposes this relative motion or tendency of relative motion between the two surfaces in contact. This force is friction. So basically, if this boy is moving this block towards the right and he is applying a force of 50 Newton on the block, then a force of friction will act such that it will also apply a 50 Newton force opposite to the direction in which the boy is applying the force, and it will tend to stop the relative motion of the block with respect to the ground. Understood? So whenever there is relative motion between two surfaces, or whenever there is going to be a relative motion between two surfaces, like that relative motion is just about to start, in that case a force of friction acts between the two surfaces such that it tends to oppose the relative motion of the two surfaces. In this case, the boy is trying to move the block, but the block has not yet started moving. But so that the block does not start moving with respect to the ground, a force of friction acts on the block opposite to the direction in which the boy applies the force. The block does not move because of friction. So why does this force, act opposite to the direction of relative motion or the tendency of relative motion? Why is there any friction at all? You see, scientists have found out that any two surfaces appear smooth in real life, but if you look at them at the microscopic level, they are not really smooth. At a microscopic level, this green block and this red block are not smooth. The edges here are like this. As you can see, they are so rough. So at a microscopic level, all the surfaces in the world are rough and uneven. So when you try to move, one rough surface over another rough surface, in that case, these protrusions of each surface get stuck inside each other and they stop the relative motion of the surfaces. Understood? So that is why friction acts. The protrusions of each body gets stuck in the protrusions of the other body, and that stops the relative motion of the surfaces. So this is what friction is all about. It tries to stop the relative motion between any two bodies. Let's now find out, what values of friction act on different bodies. Take a look at this body. This green block here is at rest on a table. There is no relative motion between the green block and the table, and therefore no frictional force acts on this green block. Understood? If there is absolutely no relative motion between two bodies, then no frictional force will act on either body. If, however, a body moves with respect to another body, a friction force acts such that it tends to stop the relative motion between the bodies. But can infinite friction force act on the body? For example, if I apply a force of 100 Newton on this block, maybe the friction force will stop the block from moving. But what if I apply a force of 1000 Newton or 10,000 Newton or 100,000 Newton? Like, till what extent will the friction force stop the relative motion between the block and the table? What is the value of the friction force, like the mathematical value? How many newtons of friction force acts on the block? Let's find that out. Limiting friction represents the maximum value of friction possible between two surfaces. Understood? So any two surfaces on this earth have a specific value of limiting friction between them. This means that between those two surfaces, that is the maximum resistance to relative motion that can be offered. Let's say that the limiting friction value between the block and this table is 50 Newton. In that case, when you apply a 20 Newton force on the block, friction will immediately apply a 20 Newton force on the block opposite to the direction in which you are applying the force. Understood? Now the limiting friction value is 50 Newton. This means that the maximum value of friction that can act between those two surfaces is 50 Newton. So since 20 Newton is less than 50 Newton, friction is able to successfully resist the relative motion between the block and the table. 20 Newton force will act both on the block and the table. It will act at the surface of contact. Now suppose I apply a force of 30 Newton on this block. Again, a force of friction small f equal to 30 Newton will again act on the block. It will stop the block from moving. What if I apply a force of 50 Newton? In that case again, friction will also apply a force of 50 Newton. After all, the maximum value of friction between these two surfaces, the block and the table, is 50 Newton. So until I keep applying a force less than 50 Newton or equal to 50 Newton, the block won't move because friction will also apply the same force in the opposite direction. Now, if I apply a force equal to 70 Newton on the block, friction will only apply a force of 50 Newton. Understood? So when you apply a force which is greater than the maximum value of friction force, then the block starts moving. Something like this. Understood? In this case, the net force on the block will be 20 Newton plus 70 minus 50 Newton. Understood? So you see that if the force I apply is less than the friction force, then friction will apply exactly the same amount of force in the opposite direction. Understood? It won't apply a greater force or a lesser force. But if I apply a force greater than the maximum value of friction force, friction will be helpless and my block will start moving. There you go. You must also remember another important point that you must remember in this case is that friction does not always act at its maximum value. So if I apply a force of 20 Newton on this green block, friction will not apply 50 Newton. It will apply only 20 Newton. So friction only acts in such a way as to prevent relative motion. Understood? It does not always act up to its maximum value. It acts only to such an extent as to prevent the motion of the block. This is another point you must remember. There are two types of friction that you must study. These types are static friction and kinetic friction. You see, there can be two cases when a force is applied on a block. The block can be at rest or the block can start moving. If the force applied is less than the limiting friction, the block will be at rest. If the force applied is greater than the limiting friction, the block will start moving. The friction force acting on the block when the block is at rest is called static friction. Understood? This friction force can have many different values depending on the force capital F. The force that acts on the block, the friction force, when the block is moving is called kinetic friction. Understood? So if I apply a force on a block and the block does not move, then static friction is acting. If the block moves, then we say that kinetic friction is acting. These are simply terms, to understand friction better. Now let us go deeper and understand more about limiting friction. The value of limiting friction between any two surfaces is given by the formula μs into n. Here μs is a constant for any two pairs of surfaces. It is called the coefficient of static friction. Understood? The value of μs is generally less than 1. This means that the value of μs between this green block and this table could be 0.5 or it could be 0.7, something like that. N here represents the normal reaction between the two surfaces. So the maximum value of friction possible between two surfaces is the coefficient of static friction into the normal reaction between the two surfaces. Understood? So there you go. Now we can simply state that if the force applied on the block is less than μs into n, which is the maximum value of friction or limiting friction, in that case the block won't move, isn't it? Because the force applied is less than the maximum value of friction. If however the force applied is greater than μs into n, it is greater than the maximum value of friction force, in that case the block starts moving, isn't it? That's how it is. μs into n, this value determines whether the block will move or not move. Another fascinating fact is that kinetic friction is not the same as static friction. This means that the maximum value of friction force possible is μs into n. But once the block starts moving, then the friction force that acts on the moving block is not μs into n. If I am applying force capital F on this block and this capital F force is greater than the limiting friction μs into n, in that case this block will move. But when the block moves, then the force small f the force of friction will not be equal to mu s into n. It will suddenly change as soon as the block starts moving. It will become equal to mu k into n, where mu k is the coefficient of kinetic friction, which is different from the coefficient of static friction. Understood? So basically, when a block moves, the friction force that acts is mu k into n. When a block is stationary, the friction force that acts is equal to the force applied if the force is less than mu s into n, and it is mu s into n when the block is at rest and the force applied is greater than mu s into n. I know all this sounds complicated, so let us consider another case and let us understand mu s and mu k and friction force better. Take this block of mass 2 kg placed on the table. The value of mu s between this block and the table surface is 0.7, and the value of mu k, the coefficient of kinetic friction between this block and this table, is 0.6. Understood? Now, the weight of the block is 20 Newton, and so the normal reaction will also be 20 Newton, isn't it? Because the block is at rest in the vertical direction. The value of limiting friction is mu s into n, that is 0.7 into 20. That is 14 Newton. The value of kinetic friction is slightly less than the value of limiting friction. It is mu k into n, or 0.6 into 20. That is 12 Newton. Now let us see what happens to this block as we apply different forces. First, we apply a force of 10 Newton on the block. The limiting friction will now be considered because the block is currently at rest, isn't it? Kinetic friction is only considered when the block is moving. So now, the maximum possible friction force is 14 Newton and we are applying just 10 Newton. So friction of 10 Newton will act on the block and it will stop the block from moving. Now, if we apply a force of 12 Newton on the block, what will happen? A friction force of 12 Newton will act on the block and it will still stop the block from moving. What if we apply a force of 14 Newton on the block? In this case, again, a friction force of 14 Newton will act on the block and it will again stop the block from moving. That is because the limiting friction value is 14 Newton. Now, if a force of 15 Newton acts on the block will start moving because the value 15 Newton is greater than the limiting friction value. But when the block moves, a force of 12 Newton acts on the block. Understood? Note that a force of 14 Newton won't act on the block because once the block starts moving, the friction force decreases from 14 Newton to 12 Newton and kinetic friction starts acting on the block. So there you go. We have exactly understood what happens and how friction force starts acting on a block. To further grasp these concepts, let's solve a problem. Of course, you can solve more such problems and understand the theory better in the physics section of TopCoaching.com. Two blocks of mass small m and capital M are placed one over the other as shown in the figure. The coefficient of both kinetic and static friction is mu. Find the maximum horizontal force that can be applied on mass small m for both blocks to still move together. As you can see, there is a smooth surface on which a mass of capital M is placed and then a mass of small m is placed over the mass of capital M. A force F is applied on the block of mass small m. The coefficient of both static and kinetic friction between small m and capital M is mu. We are asked the maximum value of force capital F for which the mass small m and the mass capital M will move together, that is, for which there will be no relative motion between mass small m and mass capital M. This definitely sounds to be a difficult question. What is happening? Let us draw the free body diagram of the mass small m first. A force capital F is acting towards the right on this mass small m. The friction force will act on this small mass m towards the left. That is because if there was no force of friction, what would have been the motion of mass small m? It would have moved towards the right and it would have slipped over the surface of capital M mass, isn't it? It would have moved towards the right and the mass capital M would have remained where it was, isn't it? But because there is friction tries to prevent this relative motion and so it tries to keep mass small m where it is with respect to the mass capital M. So it acts backwards. So these two forces act on the mass small m. If you look at the motion of the mass capital M, friction will act towards the right on it. Why is that so? If there was no friction force, what would have happened? Mass small m would have moved towards the right with respect to the mass capital M, isn't it? Therefore, relative motion will be reduced if the mass capital M also moves towards the right, isn't it? Because if there was no friction force, then mass small m would have moved to the right. So, to make sure that there is no relative motion between mass small m and mass capital M, the mass capital M should also move to the right, isn't it? That is when there will be no relative motion. So, to prevent relative motion, friction force acts towards the right on this mass capital M. I know this can be a tricky concept, so you can relax and just try to visualize once again exactly how friction tries to prevent relative motion between the blocks. Try to think along this line. What if there were no friction force? In what direction would mass small m move? How would mass capital M behave? Then try to see how friction tries to, prevent the relative motion of both the blocks. It acts backwards for the mass small m and it acts forwards for the mass capital M. Now we want that the acceleration of both the blocks be the same. So we will say that capital F minus friction force is m into a, and small f, the friction force, is capital M into a. By solving these equations, we get the value of the force capital F as small f into m plus m by m. Now, what is the maximum value of this force capital F? That is what we want to find out. Clearly, this force capital F is proportional to the friction force. So, the force capital F will be maximum when the friction force is maximum. So, instead of small f, we can put the limiting friction value, that is mu into n or mu into mg in this case, isn't it? Because the friction force will be mu into n and the normal reaction will be equal to mg, isn't it? When we balance the forces in the vertical direction for the block of mass small m. Therefore, the net force F that must act on the block of mass small m is mu mg into capital M plus small m divided by capital M. This is the maximum value of force for which small m and capital M blocks will move together. There will be no relative motion between these blocks. If the value of capital F is greater than this force, in that case, friction will not be able to stop the slipping between these blocks. What will happen in that case is that the acceleration of small m mass will be greater than the acceleration of capital M mass. Friction will not be able to provide enough acceleration, to the capital M mass so that relative motion does not take place. Understood? So there you go. Here's yet another problem. Find the minimum force F and the angle with the inclined plane it should be applied at required to pull the object of mass m up the incline of inclination alpha. The coefficient of static friction between the block and the inclined surfaces is mu. In this case, we are basically given an inclined plane with an inclination alpha. We are also told that there is a block of mass small m placed on the inclined plane. There is friction between the surface of the block small m and the wedge. We are asked to find the value of the force F that must be applied on this block of mass small m and at what angle this minimum force should be applied to pull the block of mass m up the plane. What do? We again balance forces. These are the forces acting on the block of mass small m. We are applying a force capital F pulling the mass m up the incline. The normal reaction acts perpendicular to the mass small m. Mg acts downwards and friction tends to pull the mass small m down the plane because it tends to oppose the relative motion between the mass small m and the wedge. So it tries to oppose the pull of the force capital F up the plane. Now in this case, we want to find the value of capital F and we want to find the value of beta, the angle at which this force capital F is applied with respect to the inclined plane. But why should we apply this force capital F at an angle with the inclined plane? Why can't we directly apply this force, parallel to the inclined plane as we pull the mass m up? This is because we want to find the minimum value of force F to be applied. Now you see, the minimum value of force F to be applied also depends on the friction force, isn't it? Because friction is the only force that is resisting force capital F. Friction depends on the normal reaction also, and the normal reaction decreases as we increase the angle beta, isn't it? After all, if you observe carefully, you will see that n plus f sine beta is mg cos alpha, isn't it? N plus f sine beta is mg cos alpha, or n is mg cos alpha minus f sine beta. After all, mg cos alpha is the component of the gravitational force perpendicular to the plane. F sine beta is the component of the force capital F perpendicular to the plane. So the normal reaction is mg cos alpha minus f sine beta. So the greater the angle beta, the lesser the normal reaction. Friction force's maximum value is mu n. So the greater the angle beta, the lesser the value of the friction force. Isn't it? There's no doubt about it. Because the greater the angle beta, the lesser the normal reaction. So lesser the value mu n. So basically, increasing beta also decreases the friction force. On the other hand, decreasing beta, or applying the force parallel to the plane, also means that a greater component of the force capital F is opposing the friction, isn't it? If we increase beta to a very large extent, then the force capital F that is opposing the friction, F cos beta, that will decrease. So that is why there is a special angle beta at which minimum value of force capital F must be applied, and we have to calculate that angle beta also. Understood? So did you understand why we can't directly apply the force capital F parallel to the plane or perpendicular to the plane? We have to find the angle beta at which the value of force capital F is minimum. By balancing forces, we say that F cos beta minus mg sin alpha minus F equal to 0. Isn't it? After all, parallel to the plane, F cos beta acts, friction force F acts, and mg sin alpha also acts. Now we want the minimum value of force capital F so that the block small m moves. And for this block small m to move, the maximum value of friction force must act. So we put small f, or the friction force, as mu into n. When we substitute the friction force as mu n, and when we solve these equations, we get the value of the maximum value of the force capital F that must be applied to move the small block m up the plane as mg into u cos alpha plus sin alpha divided by cos beta plus u sin beta. This is the minimum value of the force capital F. Since we want to find out beta such that this force is also minimum, therefore we can differentiate this expression with respect to beta to get the value of beta for which even this expression is minimum. When we do that and we put df by d beta equal to 0, we get the value of the force capital F as this expression. This is the value of the minimum force that must be applied at an angle beta with the incline to make the block of mass small m move up the plane. This force is mg into mu cos alpha plus sin alpha divided by square root of 1 plus mu square. When you substitute this value here, you get the value of beta in this expression. Understood? So basically, this question again seemed complicated, but all that it involved was balancing forces on the block of mass small m. Here's yet another example to clear your concepts even further. A block of mass 0.1 kg is held against a wall by applying a horizontal force of 5 Newton on the block. Something like this. So there's a block of mass 0.1 kg, a force 5 Newton is applied on the block. The coefficient of friction between the block and the wall is 0.5. Then what is the magnitude of the frictional force acting on the block? Let's find out. There is this block of mass 0.1 kg that is pressed against a wall. Mu is 0.5 between these surfaces. A force of 5 Newton is being applied on the block. What is the magnitude of frictional force acting on the block? Let's balance the forces in the x and y directions. The force in the x direction is 5 Newton towards the right and the normal reaction towards the left. The friction force is acting upwards and the gravitational force is acting downwards. It is equal to 0.1 into 9.8 meter per second square, that is 0.98 Newton. The friction force is acting upwards because it is trying to prevent the relative motion between this block and the wall. Isn't it? The block tends to fall down because of the gravitational force and the friction tends to not allow the block to fall down. Balancing these forces, we get F is 0.98 Newton and normal reaction is 5 Newton. Now the important fact here is this value of friction less than mu n or greater than mu n? After all, if this value of friction is greater than mu n, in that case, the block cannot even be held at rest against the wall. Maximum value of friction is mu n, and n is 5 Newton. So the maximum value of friction is 5 into 0.5, that is 2.5 Newton, isn't it? So the friction force can be equal to 0.98 Newton, which is less than 2.5 Newton. So the value of friction force acting on this block is 0.98 Newton. Note that the value of friction force, here is not mu n. It is not 2.5 Newton. It is less than 2.5 Newton. So friction is not always equal to mu n. Remember that. The maximum value of friction force is equal to mu n. If that much friction is not required, that much friction will not even act on the body. Here's yet another problem. This one was asked in IIT JEE 2003. What is the maximum value of the force F such that the block shown in the arrangement does not move? You can see that there is this floor here made of wood. There is a red block placed on the floor. The coefficient of friction between the red block and the floor is 1 by 2 root 3. A force capital F acts at an angle 60 degrees with the horizontal and tends to move the block towards the right. The mass of the block is root 3 kg. We have to find the maximum value of the force F for which the block does not move. Again, in this case, all we have to do is balance the forces on this block. These are the forces acting on the block. The force F acts like this at an angle 60 degrees. The normal reaction acts upwards. The weight of the block is 10 root 3 Newton and it acts downwards. This is because the mass of the block is root 3 kg, and so 10 root 3 Newton is the weight of the block. The friction force will act parallel to the surface of contact, and it will act such that it will tend to oppose the relative motion between the surfaces. Since the force F tries to move the block towards the right in the horizontal direction, the friction will act parallel to the surface towards the left, isn't it? By balancing the forces, we can say that 10 root 3 plus F sine 60 degrees is N in the vertical direction. In the vertical direction, gravitational force 10 root 3 Newton is acting downwards. The normal reaction N is acting upwards, and the vertical component of the force capital F is also acting downwards. So F sine 60 degrees plus 10 root 3 is the normal reaction. In the horizontal direction, N equal to root 3 by 2 into 20 plus F. On simplifying this expression, we get N equal to root 3 by 2 into 20 plus F. In the horizontal direction, F cos 60 degrees is the force applied on the block, and this force is balanced by the friction force. So F cos 60 degrees is equal to F, or capital F is equal to 2F, since cos 60 degrees is 1 by 2. So we basically have two equations here. Now from this equation we can see that capital F is 2 times the frictional force. We want the maximum value of capital F, isn't it? So therefore the maximum value of capital F will be 2 times the maximum value of frictional force. The maximum value of frictional force is mu into N, isn't it? That is coefficient of friction into normal reaction. Mu is given in this question. When we substitute the value of mu and when we solve these two equations, we get the value of the maximum force capital F that must be applied at an angle 60 degrees to the block to keep the block at rest as 2 mu root 3 by 2 into 20 plus F. On simplification, capital F comes out to be 20 Newton. So basically the maximum force that can be applied at an angle of 60 degrees to this violet block is 20 Newton. If a force greater than this force is applied, then the block will start moving. Here's yet another problem. This one was asked in IIT JEE 1978. As you know, in the case of friction and in the case of force problems, the more problems you solve, the better you get. To solve more problems, to attempt different tests, do log on to our website TopCoaching.com. Here's the next problem. In the figure, the blocks A, B and C have masses 3 kg, 4 kg and 8 kg respectively. The coefficient of kinetic friction between any two surfaces is 0.25. A is held at rest by a massless rigid rod fixed to the wall, while B and C are connected by a light flexible cord passing around a fixed frictionless pulley. This is the figure given in this problem. As you can see, there are three masses A, B and C. A is held at rest by a rigid rod with joints A to this wall. Understood? A force capital F acts on C towards the left. B and C are connected by a massless string that passes through a pulley. Find the force capital F necessary to drag C along the horizontal surface to the left at a constant speed. Assume that the arrangement shown in the figure, that is B on C and A on B, is maintained throughout. So basically, we have to find the force capital F such that C gets dragged along the horizontal surface with constant velocity. Understood? This is what we have to find. The question appears to be bamboozling at first glance. What will we do here? The first interesting fact that we must note is that the net force on all the blocks here is 0. Why is that so? You see, if block C moves towards the left with constant velocity, then obviously block B must move to the right with constant velocity. The net force on block C is 0 because it moves with constant velocity, it has 0 acceleration. The net force on block B is also 0 because it moves to the right with constant velocity, because the string has the same length, isn't it? So if C moves to the left, B must move to the right with the same constant velocity. We had studied that in case of fixed pulleys, isn't it? So B and C both have net force equal to 0 on them. A has net force equal to 0 on it because it is attached by means of a rigid rod to the wall. So the net force acting on all these three blocks is 0. Now let's look at each block and draw the free body diagram. Let's say the tension acting on block A is T dash. The normal reaction acting because of block B on block A is N3. The net weight of block A is MA into G. Block B is definitely moving, isn't it? Block B is moving at constant velocity to the right. Therefore, maximum friction acts on block A towards the right. Understood? Why does it act towards the right? You see, if there was no friction, then B would have moved to the right and A would have remained where it is. But friction wants to stop the relative motion between A and B. So it will try to move A also with the same velocity with which B is moving. Understood? So that there is no relative motion between A and B. So friction on block A acts towards the right and it will be equal to mu N3. We can write the equation N3 equal to MAG in the vertical direction because A is at rest. We can say that N3 is therefore 30 Newton. Understood? In the case of block B, if you observe carefully, tension acts to the right. This tension is T. N2 force acts upwards and MBG, the weight of block B, acts downwards. N3, the normal reaction because of block A, also acts downwards. N2 is the normal reaction because of block C on the block B. Now block B is definitely moving to the right. Therefore, the friction force acts on the top of block B towards the left. And maximum friction force acts F3 equal to mu N3, and friction force also acts on the surface between block B and block C towards the left. So two friction forces act on block B. One is the friction force between the AB surface, and the other force is the friction force between the BC surface. Both these friction forces try to bring block B at rest with respect to A and C. But block B is moving towards the right because block C is moving towards the left. That is given in the question. And for the length of the string to be constant, if block C is moving to the left, then block B must move to the right. And maximum value of friction forces act because block B is definitely moving. When we balance these forces, we get N2 equal to N3 plus MBG in the vertical direction. We already know the value of MBG because the mass of block B is given. We just found out that N3 was 30 Newton. So N2 comes out to be 70 Newton. Understood? We can also write down the forces in the horizontal direction. Since block B has 0 acceleration, net force on it is 0. So T minus F2 minus F3 is 0. The value of F2 is mu N3. The value of F2 is mu N2. Mu is known, N3 is known, N2 is known. So the tension force on block B comes out to be 25 Newton. Now we can draw the free body diagram of block C. Tension force T acts on the block C because the string is massless. So the tension force acting on block B and block C must be the same. A normal reaction force N1 acts on the C from the ground, and a force MCG acts downwards. That's the weight of block C. A force N2 acts on block C from block B. The force capital F, of course, acts towards the left. Again, since block C is moving, friction force acts on block C. Note that the friction force on C is again on two surfaces, the surface BC and the surface of contact between C and the floor. The friction force F2 between B and C is mu N2, and it's towards the right because the block C is actually moving towards the left. Similarly, the friction force F1 between C and the ground is also towards the right because the block C is definitely moving with a constant velocity towards the left. So we can balance the forces on block C2. In the vertical direction, N1 is N2 plus mcg. The value of mcg is known and N2 was what we found out in the previous slide. So N1 comes out to be 150 Newton. We can also balance forces in the horizontal direction since the net acceleration of block C is 0. So F minus F1 minus F2 minus T is 0. F1 is known, F2 is known, and tension was what we calculated in the previous slide. So the value of capital F, the force that we are applying on block C, comes out to be this expression, 80 Newton. So the answer for this problem is 80 Newton. You must have seen, that this problem touched upon the core concepts of friction. It made you understand, why friction act at its maximum value, in which direction will friction act, and why. All these concepts are cleared by this problem. Of course, for more such problems and more tests related to friction, you can always log on to the physics section of TopCoaching.com. For now, let's move on to the next concept used in this chapter, the angle of friction. The angle of friction represents a fascinating friction concept. Sometimes friction is referred to as the tangential reaction. You see, friction acts parallel to the surface, isn't it? If there are two surfaces in contact, then friction acts parallel to the surfaces. Normal reaction, on the other hand, always acts normal to the two surfaces in contact, and both of them are contact forces. Both of them act when two surfaces are in contact. So normal reaction is called normal reaction, and sometimes friction is called the tangential reaction. Sometimes scientists like to calculate the net reaction force between two surfaces by calculating the total reaction, that is, the resultant of the friction force and the normal reaction force. Can you see that here? This is the total reaction. The angle made by the total reaction with the normal reaction is called the angle of friction. Understood? So lambda here represents the angle of friction. This is one other concept that you must remember. The angle between the total reaction, the resultant between the normal reaction and the friction force, and the normal reaction is called the angle of friction. Let's now solve yet another problem. This problem was asked in IIT JEE in 1997. Block A of mass m and block B of mass 2m are placed on a fixed triangular wedge by means of a massless inextensible string and a frictionless pulley as shown in the figure. The wedge is inclined at 45 degrees to the horizontal on both sides. The coefficient of friction between block A and the wedge is 2 by 3, and that between block B and the wedge is 1 by 3. So this is the wedge shown in the figure. As you can see, the angle of incline on both sides is 45 degrees. A block A of mass m is placed on the wedge and a block of mass 2m is placed on the wedge. A pulley connects these two masses with a massless inextensible string. The coefficient of friction on both surfaces is given. If the blocks A and B are released from rest, find the acceleration of A, the tension in the string, and the magnitude and direction of the force of friction acting on A. Well, this question really seems to be mind-boggling. What's up? Well, in this question, as you can see, there is mass A, there is mass B, and there is this wedge. We have to find the acceleration of the blocks, which will be the same because they are connected by a single string, the tension in the string, and the friction force acting on the blocks.